Okay, so let's get started. Okay, today we are going to go back to the modeling topics that you briefly studied at the beginning of the course. In particular, we're going to go back to finite state machines, modeling with finite state machines, and we'll see how you can extend the basic finite state machine model to reason about systems that also have continuous components. Okay, and those systems are called hybrid systems. And the particular modeling technique that we learn about today is called hybrid automata. Okay, so let's do a quick recap of why modeling with state machines is useful. Recall last time we talked about interrupts, and we reasoned about this really simple program which could go wrong in so many different ways, right? And it wasn't trivial to think about all the assumptions that you need in order for the program to work correctly. And so you can imagine as you scale to larger programs and you have more interrupts with different priority levels, thinking about the correctness of such programs gets really hard. So that's where state machines come in. State machines are a convenient way to model the system so that an algorithm, a program, can then go and analyze those state machines, say one for the main program, one for the ISR, maybe one to model the hardware that deals with raising interrupts. And then it combines all these state machines and does analysis which tells you whether there are bugs, and if there are bugs, how things can go wrong. Okay, and this can be really, really useful. We will study these topics in April. That is how, given a bunch of state machines, you can check whether the combination of those state machines works correctly or not. Okay, so that's one reason why state machines are really useful. But then even as you do your design projects, and even in the lab now, modeling with state machines is useful because it often helps you avoid problems down the line. So in the last 3 years of teaching this course, we always have students give us feedback at the end of the course as part of their final project reports. And it's always the case that people say that modeling with state machines or whatever they used helped them avoid bugs, which otherwise, they found other teams getting stuck with. Okay, so modeling is really useful. You saw earlier in the lecture on state machines that you can use state machines not only to model the system that you're interested in, but also to model the environment of the system. So we had this example where you have a traffic light controller, and then you have a model of the pedestrian. And the pedestrian model is the environment for the traffic light controller, right? So modeling the environment is another use of state machines. We'll talk about, now that you have a model for the system and a model for the environment, you have to combine them in some way. You have to show that if you come up with a state machine that corresponds to the two talking together, right, communicating. And so we will, maybe at the end of today's lecture, but definitely at the start of next week's lectures, we'll talk about how to compose or combine subsystems that are state machines to make bigger state machines. And then in April, we'll talk about the algorithms that we'll use to check whether a system satisfies its specification, that is, what it's supposed to do in its operating environment. Okay, so these are some of the uses of state machines that we will go through in this course. So I want to start with a quick recap of the material on state machines that you've seen. It's been, I think, about 2 weeks since you last saw the materials in a lecture, so I'll just go through a few slides to recall that. So the standard notation for FSMs is you have these circles or bubbles, and these represent states. And then you have edges that go between the bubbles, and those are transitions. So remember that if you have a bunch of states, if you have a deterministic state machine, then one of them is the initial state. So you start in one of those states, and typically you indicate that by this arrow coming in from outside. Okay, so that's the initial state. And then every transition here has an associated guard and an associated action. Okay. And the guard tells you when this transition can fire, when this reaction can fire. And the action tells you what happens when the reaction fires. Okay? And then some transitions can be self-loops. And you also learned about stuttering, which is the property of the state machine staying in the same state and doing nothing, right? Produces no output. Okay, so I don't know if one point was discussed, which is how long does it take for a transition to happen? So what do you think? Really fast, okay, Rafael? Right, so this is a model, and so how long a transition takes indeed depends on what is done on that transition, right, which in turn depends on the implementation. Now, but we're talking about modeling right now, and a convenient modeling technique is to assume that the transitions are instantaneous, right? So once the guard is true and you leave state 1, you enter state 2 at that very instant, and the action happens alongside, so it happens instantaneously. Now this is not completely realistic, right? The action that you have on this transition could be a whole program that's doing pretty complicated stuff, right? So modeling this is just an abstraction of the real system, so you have to keep that in mind. But if indeed the action was doing a lot of work, right? It took a significant amount of time. Maybe you shouldn't model it as a single transition, right? If you really have to reason about about how long that transition takes, and that's important to the correctness of the system, maybe you shouldn't model that action as a single transition, and maybe you should break it up into states where the program runs inside the state. Okay, so you have to think about these things when you construct the model. Typically, the reason we assume that transitions are instantaneous is when you construct a model of a state machine like this, the time that it takes actions that are labeled on the transitions is typically much, much smaller than the time the system spends between transitions. Okay, and so you can make an abstraction that the time it takes a transition is instantaneous, it's 0, and the time it spends in states could be much bigger than that. Okay, so that's one thing to keep in mind. All right, so so you saw this example. I think this is the first example that was presented in class of a system that counts cars coming in and out of a garage. And so when you're presented with a diagram like this, the first place to start is at the inputs and outputs. So you look at what are the input signals here and what are the output signals. And so there are two inputs, up and down, and these are pure signals. So each of them is either present or absent at any given instant. And the output is a single output, which is an integer that goes from 0 to m. And here we haven't explicitly given it a name, but the value of the output is indicated here on the right-hand side of the slash, right? So so now with this notation, you have m plus 1 states, right? Each state corresponds to a particular number of cars being in the garage. And to remind you, this notation, we write it as a Boolean expression. So this is up and not down. And this means that the up signal is present and the down signal is absent, right? And when that's true, then you have a car coming in and no car going out. And so you make a transition, you increment the count and make a transition to the next state. Okay. Now, notice that if m was, let's say, 1 or 2, then you could draw this diagram very easily. But if m is 2 to the 16 or something like that, you can't really draw this diagram, right? And so the finite state machine notation becomes cumbersome when the models you have a large number of states. And so we then saw this notation called an extended state machine. So extended state machines are essentially state machines, except that for compactness, we will introduce variables. Okay, so again, when we start reading this diagram, you start here. So this state machine has a variable called count, and the value of count is in the range 0 to m. and the inputs and outputs are the same as before. But now the diagram is much more compact. So now you have a single bubble where when you enter the bubble, you enter initializing the variable count to 0. Okay, and this corresponds to the state 0 that we had in the earlier picture. And now each time you make a transition, you have to update the value of count. In effect, you're updating the state, right? And so you first test the original guard condition, but you also have this condition that we need to add to model the fact that you have only at most m states, right? Because there's a bound on the value of count. So as long as count is less than m, you can increment it. And the output is the incremented value, and the action is the increment. And as long as count is positive, you can decrement it. Okay, so you have these two transitions, one corresponding to the increment edge in the previous diagram, and the other one corresponding to the decrement edge. Okay, so so just to make sure you all remember this example, what is the size of the state space here? M plus 1, right? It remains unchanged. Now, this is a tricky thing when you work with extended state machines. It's harder to think about how big the state space is, because you have to take into account not only the number of bubbles, but also the combinations of values that go with each bubble. Okay? So for state machines, we have this extended notation where you have a variable declaration alongside the declarations of input and output signals. And you have to think, if you're going from a vanilla state machine to an extended state machine, you have to think about what are the additional updates you have to make to all the variables, and you have to add those in the actions. Okay? Actually, it's more often the case that people start with extended state machines because it's quite natural for those of us who've grown up with programming languages to just write variables directly as part of your model. Okay, so so now let's look at another example that you've seen. This is the traffic light controller, and here we have a variable that called count, which is modeling a timer, right? So count takes values from 0 to 60 because in this model we want to be able to count 60 seconds. Okay. So recall that in state machines you have these default transitions, and the meaning of the default transition is that the guard is implicit. The guard is essentially the negation of the guards of all the other outgoing edges from that state, right? So the default transition is taken when none of the other transitions are taken. And so what happens in this diagram is you initialize count to 0, and then on every transition, the default transition, as long as you stay in the state red, as long as the signal stays red, you keep incrementing count. Okay, so so there is this issue with state machines that the picture itself doesn't tell you when a reaction happens, right? And I think this topic was touched upon, but we'll talk about it in a little bit more depth today. So so for instance, here there's an implicit assumption that count, this increment has to happen once a second, and therefore this transition must be taken once a second, right? And this is called time triggered because the instant the transition occurs, when the transition occurs, is dependent on the passage of a certain amount of time, and that defines when the transition occurs, right? But it's really implicit in this diagram. Nowhere does the diagram specify this fact. Right? This has to come outside the diagram. And so this is another thing that you have to be careful. When you draw a state machine diagram, make sure that you also think about when the transitions happen. And is it time triggered or is it event triggered, okay, which is the other way. So here, for instance, if we assume that one reaction or one transition happens per second, then we know that we initialize count to 0 here, and on every transition, count will get incremented. And so after 60 seconds, count will reach 60. Okay, and then this transition gets enabled. Count is greater than or equal to 60, and then you can go to green outputting the signal green and setting count to 0. Okay, so here there's another slightly vague component of this diagram, which is this says count greater than or equal to 60, right? It doesn't say count equals 60. So can I, for instance, stay in the red state for 61 seconds and then make a transition? What do you think? Yeah.
So I think you went to something like this a lot, because when you something like you skip a count or something based on external factors. So that was because we found that when we set stuff like exactly equals something.
Okay. All right. So that's a good point. So what Rafael said was that if you set a guard to test if a variable equals a value, right? Then it's a very brittle condition, right? It might be that the variable equals the value, but if it's a sensor value, especially if the variable stores a sensor value, there could be a little bit of noise in the value. So you should be able to tolerate plus or minus some epsilon, right? And if you just check if the sensor value equals 0, for example, well, it may not be 0. It may be 0.001, and the equality won't hold, and therefore you will miss the condition, right? So oftentimes in embedded software, you will see that people don't actually use equality for guards. They use greater than or equal, or they may have an interval. So it might be if it's within a certain interval, 60 minus epsilon, 60 plus epsilon, then the transition is taken. Okay, so this is often done, but the implicit part of this picture is that this transition is taken as soon as it's enabled, right? And so as soon as count exceeds or becomes greater than or equal to 60, you make that transition from the green state to the red state. This is another thing which is not explicitly stated in the diagram, okay? But it's one of those things that you have to, when you're using some modeling technique, let's say you use a tool like the ones you're using in the lab, right? So there are tools like Simulink and Stateflow, LabVIEW, and so forth. Let's say you use some other tool in the future, and they have a state machine modeling technique, right? And you want to use that. You have to read the manual, or ask the people who designed the software all the details of what these things mean. When is the transition taken, right? Is it when the guard becomes as soon as the guard becomes enabled, or is there some other semantics to it? What is the semantics of default edges? Okay, how often are transitions taken? So in this case, is it time triggered? Is it event triggered? Okay, you need to look at the details to see what exactly that modeling tool provides you. Yes, Nima.
So if we are counting up, and at that moment, like some other event happens, and we are transiting from that state to another state, can we mess up our count somehow?
Okay, so the question is, you're counting up, and you're in the process of incrementing the count, or okay. Another event happens. Okay.
Yeah.
Okay.
So in the middle of counting up, can we mess up our counter instead, and then we hit the interrupt rule answer?
Okay. Okay. So this question goes back to Tuesday's lecture on interrupts. So suppose you are in the process of taking an action, and let's say you're counting up, and an interrupt happens, right? Then whether you interrupt the count increment depends on whether the interrupts are enabled. Let's say they are enabled, right? Then if you are in the middle of some code, let's say more complicated than count interrupt, right? Then in general, yes, you would suspend that code and then jump to the interrupt service routine and start executing it, right? So it's entirely possible that you're in the middle of executing a transition in the implementation, right? And that's not instantaneous, and it's running some code, and some other interrupt happens, right? And you have to be able to service that interrupt. Now, this is one of the tricky things with modeling with state machines, because we assume that these edges are instantaneous. So again, if there's code running which will take a certain amount of time, it's best to model that as a state, right? And then you will have to model the occurrence of an interrupt as a different state machine that runs concurrently with the original state machine, right? And as we'll see in the next lecture, you have to combine these. You have to compose these two state machines. And then when you compose them, you will see all possible behaviors, including the behavior you've described, which is you're running a piece of code, and then you get interrupted in between. And you'll have to follow that path in the combined state machine to see what happens. OK? Yeah.
So this entire idea of state machines is an abstraction above the actual code.
That's right.
Right. So in the lab, though, we were literally using encoding of states in the program.
That's right.
How do you? That doesn't seem to agree with the abstraction that was just made. Like the state machine is an abstraction. The code is not directly in states.
OK. So this is a good question. So the question is that in the lab, as you're doing the hill climb lab and probably in your other projects, you will often be encoding state machines directly in C code. So you will have a switch statement which has a bunch of cases that model a state machine. Okay, so let me try to describe an example. So suppose you have something like case. Let me rewrite this. Okay, so suppose you have a switch statement with a bunch of cases. So let's just call them integer values. So case 0, case 1. It's not showing up. More network problems, I guess. Weird. Okay, there we go. All right, so when you code in C, you will code up a state machine as a switch statement, and every state, right, will be a case in the switch statement. But it's not really a state of the state machine. It's not an entire state of the state machine because you'll have other things going on, right? So let's say you have another variable x, which in this state you assign to y plus z, for instance. The value of x and the value of y and the value of z are also part of the state, right? So the entire state of your machine has to comprise not only the value of this variable that you're switching on, but also the value of every other variable in your program, okay? And so when you're modeling, that model is an abstraction, but the tools that are used to check bugs based on state machine models, their models will take into account the entire full-blown state. Okay, and so I guess so. Going back to your original question. So that was regarding in the lab you're modeling with state machines, and can you remind me what the original question was?
Yeah. So if the state machine model is an abstraction,
right?
Doesn't that imply that you're not supposed to code directly in states?
Okay. So if the state machine model is an abstraction, okay. So I'm trying to understand the question. So the model you create here is certainly an abstraction of the code, right? But when you're coding, right, you're implementing some state machine as a program, right? If you take that switch statement and all the variables there are finite, right? Then what you have is another state machine. It may not correspond to this bubble model exactly, but
if you took your model state machine
right,
and implemented that directly, should it correspond?
It should correspond. It should correspond. That's right. But what you should do is then make sure that if the assumption is that a transition is instantaneous here, then a corresponding transition there is also instantaneous. So going back to this picture, right? Here the question is, how would you model a transition? Would it be from going from one case to another case, or would it be from going from the machine instruction for this case to the next machine instruction, right? What the algorithmic tools that do this analysis on state machines, they would go from a machine instruction to machine instruction, right? So at that level, it would be safe, right? So that's the real semantics of the code you wrote, right? It's at that level of a state machine. But this high-level model that you created is still useful as a guide for you to reason about higher-level decisions. Like, let's go back here. So here, for instance, if the property that I'm interested in about this design doesn't depend really on how long this transition took, but it just is something like I will always cycle through the lights in the order red, green, yellow, right? But I'm not saying when it happens or anything like that. Then looking at this model, you can convince yourself that that indeed does happen, right? And so it depends upon really I guess the way design typically occurs here is you create a high-level model and you prove some properties that hold in that high-level model. But there are properties of the implementation of that model which you can't say anything about yet, right? Then from that high-level model, either manually or automatically, you get code. You have to rerun some checking on that code, some tests on that code to ensure that the code has the same properties that you intended for the high-level model, right? And so you have to check it again. It's not sufficient to just start with the high-level model. Now, if that process of going from a high-level model to code is automatic, then you would hope that the tools, that the compiler that does that automatic translation has correctness, right? Somebody has proved that this translation will preserve a bunch of properties, okay? Unfortunately, that's not always the case, and so you still have to run code-level checking tools, okay? In this variable count, yeah. No, you also have to know whether it's red or green or pending or yellow. Yeah.
Does that have to be part of the
Does well that okay? So the question is, in this model, the state is not only the value of count, but it's also the bubble that you're in, right? So it's going to be, the state is going to be a tuple comprising of takes a while to refresh. Okay, so the state is going to be a tuple. Let's call it mode, which is the bubble you're in, and the value of count. Okay, so the state is mode comma count, there are 4 possible values for this and 61 possible values for that, right? So that's your state space. So now when you actually implement this, you will have a variable. Let's say you implement in C code, you will have a variable for mode, okay, which will take one of 4 values. So maybe it's an enum type or something like that, right? And so that entire thing will be your state.
When you're in the pending state, our count can go even higher.
Okay, let me remind me of that model. So when you're in the pending state,
The count can just go up, right?
so this is a good question again, right? So if you're in the pending state, you have this edge which is count greater than or equal to 60, right? In principle, you would think the count can go beyond 60, but under the assumption that we take a transition as soon as the guard is enabled, right? The count doesn't exceed 60. Okay? Yeah, question?
It's just kind of a nosy. It seems like the pending state isn't necessary at all because the pedestrian doesn't do anything. So why do we model it? Is it just like...
Oh, so why is there a pending state, right? So can anyone tell me why we have a pending state? Yeah.
We want the green light to last at least 60 seconds so the traffic keeps flowing.
Okay, exactly. So we want the green light to last at least 60 seconds. So, but if, let's say, 30 seconds have elapsed and a pedestrian comes up, you have to remember that a pedestrian was there, right? And so, so you make if pedestrian is a pure signal, right, the instant you get that the pure signal is present, you want to remember it because it might just go away, right? So think of it as the pedestrian pressing the button to indicate that they're present, right? And that button is just an impulse which says it's present or absent, right? The pedestrian might not keep holding it all the time or pressing it all the time, and so you have to remember that. Okay. Other questions? All right. So so that's a time triggered model. So again, the point here is that when the reaction happens is really here up to the environment, which is the surrounding implementation of this of the state machine. Okay. Now I think you also briefly looked at this concept of event triggered transitions. So if you have this picture where you have two states S1 and S2, and you make a transition from S1 to S2 when X is present, then this picture, again, somebody has to tell you when this is taken, right? But one semantics for this is to say that it's taken whenever X is present, right? So the event X being present is what triggers this transition, okay? And that's an event-triggered model. So if you have a state machine, you should always have not only the picture of the state machine, but something which describes when transitions occur in those state machines. Is it time-triggered or is it event-triggered? Okay, so let's look at this slight variant of that picture. So here again, you have the same two states S1 and S2, but now instead of X, I have not X, right? So not X means that X is absent. So now, would it make sense to make this event triggered? Let's see it. Yes or no? Yeah. Okay. So let's say we make it event triggered. Okay. Then the only way you can recognize an event is if for a discrete system with, let's say, pure signals, some signal is present, right? Physically, right? You need to be able to figure out if a signal is present or not in order to just define an event, right? Now, this says that the transition happens when X is absent. Well, the default case is X is absent, right? And so it doesn't really specify when to take the transition, okay? Now, you could try to augment it saying that, oh, maybe this happens at the earliest instant when I detect that X is absent or something like that. But that's also problematic because time is a continuum, right? And so what's the exact instant? If you say, oh, from time 0 to time 0.01, right, that's when I'm going to check if X is present or absent. Well, what about 0.001, right? You can always find a point in between. So that becomes difficult.
Isn't there also a problem if an event happens during another event? You have multiple events firing. What order are they supposed to be processed?
Okay, so Ryan has a good point here. So this little example had only one event, which is an input event. One signal. There is an input signal, which is a pure signal. But you could have multiple pure signals, and clearly then you have Boolean combinations of events being present and absent, right? And let's say there are two events X and Z that are both present, but they're present at different instants, right? So which one do you react to? Do you react to the first event that comes or the second event that comes or whatever, right? So you need to, again, that decision would depend on the model that you have, right? So, so if I had a state machine that looked like this, with one edge with X and another edge with Z, right? Then I can define this state machine to be event triggered, and it would react to the first event amongst x and z that occurs. What if x and z occur at the same time? Which one do I react to? This diagram doesn't really specify that, right? Comments?
Well, I was saying if we have that in the code, what happens is going to see. Run next person.
Okay.
Just running Z.
Okay, so the suggestion here is that if you actually implement this, well, in sequential code, you have to check for the events in some order, right? You might check for x before you check for z. So if they happen at the same time, then you would execute the top transition first rather than the bottom transition. Okay, but that means that you explicitly in your code, you don't have this transition, but you have a version. So instead of this. So instead of this, you have something which is saying if x is true and not z. Okay, or actually more accurately, so you would have just x. So if x is present, and then this one would be different because it comes later. It would be if z is present and x is not present, then you make the transition, right? So that's down there. The guard would look something like that of the implementation. But if the model, original model looked like this, it really doesn't specify what to do when both x and z occur at the same time. And that leads to non-determinism. Okay? Questions? Yes?
Going back to the slide,
Yep.
this is sort of a contrived thing, but there are situations where you don't want to react as long as something is present, and you want to react to its absence. So wouldn't that model sort of situation like that?
Okay. So the
Always just flip that in your head.
right. So the question is that what if I have a situation where I don't want to react to something being present, some condition being true effectively, right? But I want to react when that condition is not true. Okay, you can construct your model accordingly. So the pure signal is present when the condition is not true, and is absent otherwise, right? So with pure signals, these pure signals are really a modeling technique, right? They don't really correspond to a voltage level or something like that. But if what you're thinking about is reacting to a change in voltage level, right? Then you should model the pure signal accordingly. Okay. All right. So in this case, going back to this example, right, where this says that you take the transition where x is absent, you can't really go with an event-triggered model here. And so you could go with time-triggered, potentially. So you say, I'm going to take the transition when the clock reaches one time unit, and if at that time instant x is not present, then I take the transition, and if it is present, I won't take the transition, right? But again, we go back to the situation there that the environment really triggers this reaction. The reaction is not triggered by the signals, the input signals to that system. All right. Okay, so that's a quick recap of extended state machines. Are there any questions before I move on to hybrid automata? No? All right, so hybrid automata are a technique for modeling what are called hybrid systems. There's a chapter on hybrid systems in the book. And hybrid systems really are, fundamentally, they're a really good way of thinking about cyber-physical systems, right? Because cyber-physical systems have both continuous and discrete components, and that's what a hybrid system is. It's a system that has both continuous and discrete components. So the high-level picture is, we've talked about discrete state machines, finite state machines, and those look like this. You have bubbles corresponding to states, and you have edges corresponding to transitions. Then we've talked about continuous systems, where a state is really a value to all the continuous variables, so say position, velocity, acceleration, things like that. And then really those state variables evolved according to some continuous trajectory, which is defined by, say, a bunch of ordinary differential equations. Okay? And so if you start in a given state and you let some time elapse, you reach some other state. Okay? Hybrid system is one which has both of these behaviors. So in a hybrid system, you have both discrete variables and continuous variables. And one of these dots, the black dots, is really a combination of discrete values to the discrete state variables and continuous values or real values to the continuous state variables. There are times where the discrete variables don't change, and what changes is only the continuous variables, and that's this kind of a continuous trajectory. And there are times when what changes are the discrete state variables, and the continuous variables might get reset. Just like in extended state machines, you might reset or the value of count. You could reset the value of a continuous variable, and those happen on these blue edges, which are transitions. Okay. Now, in various books and literature on this topic of hybrid systems, since the notion of a transition or reaction is often overloaded, they call a discrete transition a jump and a continuous transition a flow. Right. So the discrete transition is when you jump from one discrete state to another discrete state instantaneously, and a continuous transition is when time elapses and the values change, they flow gradually from one valuation to another valuation. Okay, so hybrid systems arise all over the place. Certainly they arise in cyber-physical systems where you have digital controllers of a physical system, which is typically called the plant. So think about the thermostat in your apartments or houses. You have really a digital controller. Okay, that's the discrete part, and that's controlling the heater, which is a physical system which has its continuous dynamics, right? And so that's an example of a hybrid system. There are subsystems in cars, like the intelligent cruise control, that's a hybrid system. The autopilot in a plane, that's a hybrid system because you have a digital software and digital computer component that's controlling the plane's climb and the rudder and so forth. Okay. So this is an obvious place where hybrid systems arise. Another place which is really interesting is in modeling natural phenomena. Right? So these are systems that appear in nature. You could think of them as cyber-physical systems, but they're not necessarily man-made. One example is a bouncing ball, right? If a ball bounces, if I drop a ball from here, it'll go hit the floor and then bounce back up, right? That's just a natural phenomenon, right? No software involved there. But you can model that system as a hybrid automaton, and I will go through an example of this modeling in a couple of slides. It's been shown that you can also model processes in cells as hybrid automata. Okay, so these are examples of using hybrid automata as modeling techniques to understand natural phenomena. And then finally, you may not have a single controller, but you may have multiple systems that are controlled, but they interact with each other. Air traffic control is a great example of this, right? So in air traffic control, you have the planes that are moving around. They have their own control. They have their own dynamics, and then you have these the traffic control towers at every airport, which are and air traffic control stations around the country, where they're running software that's monitoring where the planes are, and so forth. You have humans that are controlling them, so humans are part of the system, and they're giving commands to planes, descend to 10,000 feet, right? And that command is then carried out by the plane, so there's a continuous trajectory angle to that. So this is really, it's a multi-agent system because you have planes, you have controllers on the ground, and so forth. But if you want to model the system, then you need to model both the discrete components as well as the continuous components. So it's really a hybrid system. But you guys will also be doing building hybrid systems for your projects. So a lot of the projects are about robots doing fun things together, right? And you have robots, they have their dynamics. You'll be programming it in software, so there's a discrete component to it. They'll be communicating through Bluetooth or Wi-Fi or whatever, right? And so it's really a multi-agent system, and you can also model that as a hybrid system. Okay, so so what does a hybrid system look like? So let's start with a simple kind of hybrid system which only has time as the continuous component. And the version of hybrid automata that we'll use for this is called timed automaton. The idea of a timed automaton is actually relatively recent. So finite state machines have been around for 50 plus years, right? Timed automata, the concept of timed automaton was introduced 20 years ago. So it's very recent, and the theory of automata is still being developed. So it's a special kind of hybrid system. So the picture at the top level, the picture of a timed automaton looks very similar to a state machine. So you still have bubbles, and you have edges going between the bubbles. But the point is that what happens inside a state is the passage of time. Okay, so time is a continuous variable which will evolve according to a differential equation, and so you can have different time-based systems here. Typically, these continuous variables model timers that you may have in your system to do various tasks, right? So, for instance, we saw last time in the Tuesday lecture, we talked about timer interrupts, right? So you have a timer on your board, and when the timer elapses, a certain amount of time elapses, an interrupt is raised. Okay, so that's a system where time is a critical component. So let's look at a system that we all use on a regular basis, which is a mouse. Okay. Now the question is, what happens when you double click versus when you single click a mouse? Okay. How does the control software determine that you've double clicked rather than single clicked? So in general, so the way we're going to model it, again, I'll start at the top. There is an input, which is click. It's a pure signal which says whether or not I've depressed the left mouse button or not, right? And that is either present or absent. And the output is a pair of signals. Single is a signal which says it's a single click, and double is a signal, which says it's a double click, and both of them are pure signals. So when double is present, it means the system has deemed that you did a double click. Okay, and then you have a continuous variable x of t, which is a variable that tracks time. So what happens is you start with x of t, the timer variable, being set to 0, and you're in the idle mode. So in the idle mode, the dynamics is that x dot of t is 0. Okay. So what does that mean for the value of x? Doesn't change, right? So the value of x does not change. It stays at 0 as long as you're in the idle mode. Okay. But at some point, let's say a click is present. So let's say this is event triggered, right? So when a click is present, you make this transition. The action is to set x to 0. Okay, so you're resetting the timer, and then you go to this state called 1. Now in the state called 1, you allow time to elapse at a rate of 1. Okay, so x dot of t equals 1 means, what is x of t? Simply t, right? So x of t is just t. It's just tracking real time. And so the value of x at any instance is going to count the amount of time that's elapsed since you entered this mode. By the way, when we go from finite state machines to hybrid automata, the bubbles will be called modes rather than states. Okay, because the state of the system is really not just the bubble, right, but also the value of the continuous variable. So in this case, the state of the system is going to be a pair x, which is the timer variable, and the mode, right? And x of t is a real valued quantity, and the value of mode at any time t is going to be an element of I think it was idle, comma 1. Okay.
So in this case, can you define a state space? If your T is continuous, you
Mhm.
have enumeration of states.
Okay, so that's a good question. So the question is, if you have x of t, which is a real valued variable, can you have a state space? And if so, I think the implicit question is how large is it, right? So indeed, you do have a state space, right? A state space is the collection of all evaluations to x and mode that you can possibly have. So you do have a state space, but it's infinitely large, right? So this is an infinite state system. You've talked about finite state machines in the past, right? Finite state machines are machines that have finitely many states. Okay, this is an infinite state machine. It has infinitely many states. Okay, infinite state machines, you can get infinite state machines not just with real valued variables, but also with integer variables, right? There could be a counter which is just counting over the naturals. So instead of the reals, you have the naturals, and that's still an infinite number of states. Okay. So going back to this, so now in this mode, the mode 1, x is tracking time, and let's see what happens here. So if x of t becomes as big as 1, so time, at least one time unit elapses in this mode, then this transition is enabled, and the output is single, right? So so what it means is that if you've spent one time unit in this mode and there was no other click, then it must have been a single click. But if you spent less than one time unit and a click occurred, a second click occurred, then that's deemed to be a double click. So if you get 2 clicks within one time unit, that's a double click. Okay? And you go back here. And then you wait for the next click. Yes, question?
Maybe a single click occurs at less than 1.
Okay, so you only have clicks. You don't have single or double clicks, right? That's the only input. So this is what's saying that what happens in your scenario, which is you get a click and less than one time unit has elapsed. No, it'll be a so that'll be a double click, right? Right. But if let's say 1.01 seconds later after the first click you got a second click, that'll be viewed as a second single click, or at least it'll trigger a second first click, and then it'll wait. The system will wait for the second click after that.
The middle transition, don't we need to have a click as well?
This one?
Yeah.
Okay.
Or it's just good
No.
even if the
Yeah, it doesn't need the click to happen, because the what this transition is doing is it's saying that, okay, this click was a single click, right? And so by definition you couldn't have had another click which happens which happens less than one time unit after this first click. But it's possible on this transition for you to get a click at that instant, right? So so what happens in that case? Well, this basically doesn't specify it. So if x of t is equal to 1, and at that time unit a click occurred, then would we then go back here, or would we stay here? Okay. According to this logic, if the click occurred, so the transition system really says that if I'm in this state and a click occurs, I go to this. If I'm in this mode and a click occurs, I go to mode 1, right? But if a click occurred on entry, and it's not present after you've entered mode idle, you will miss it, right? So if it just so happened that click happened exactly at this time point, then and if it wasn't present after you've entered idle, then you wouldn't react to it. Now, this goes back to the issue of how long a transition takes, right? So,
What's the purpose of having the x dot t equal 0 and x dot t equal to 1?
so the question is, what is the purpose of having these two differential equations? So having this one over here, that's clear, right? You want the timer to keep track of time. So x dot of t equals 1 ensures that x is equal to t, x of t is equal to t, right? Here, the reason we stop the timer is just like a stopwatch, right? There is nothing to keep track of in this mode, and therefore you effectively, it's like you stop the stopwatch, and it doesn't have to make progress. Okay. All right. So let's go back to the thing that I was talking about earlier. So if we assume that this transition is instantaneous, which is the typical assumption, then if a click was present when you started this transition, it will be present when you end this transition, right? When you enter the idle mode. And so presumably you would react again and you would go back to mode 1. Okay? So in order for this system to react to two clicks, both spaced exactly one time unit apart, we rely on the fact that these transitions are instantaneous. Okay. Okay. By the way, does anyone know what's the typical the time delay between clicks that a mouse uses? Of the order of what? Half a second. Yeah. So that's about the typical order. At least what I checked for a Microsoft mouse, that's 500 milliseconds is approximately what they use. So that would be the corresponding thing to the one time unit that we have in this model.
So this is probably a little bit off. So what if you trigger the click, then does it mean?
Okay, so the question is, when is a click event triggered, right? So that depends on the mouse hardware, right? When it reacts to a click by the human operator, right? I don't actually know. I think you'd have to look at what a typical mouse, go to Logitech's website or something and try to get some information on when it registers a click. I think it's typically when you release it, right? But what is the exact mechanism that they would use to detect that? I don't know.
Would it be if you're holding it down that
Right. So typically it's a press and a release that corresponds to a click, right? And it's registered at the point of release. Okay, so we saw this point that the number of states of this automaton is really infinite. Okay, so this is an infinite state machine. Okay, now we can go back to the traffic light controller, and we can also turn that into a timed automaton. So previously, remember we had the variable count, which was going from 0 to 60. Here we have a continuous variable x of t. By the way, these variables in timed automata, which track time, they're often called clock variables, or they're called timers, right? So you have this timer x of t. You set it to 0, and you enter the mode red, and there x of t just keeps track of time. Okay. Now when the timer reaches 60, this transition is enabled. And when you make this transition, you reset the timer to 0 and you repeat the process. So again, the timer starts, it tracks time, and the process continues. So you'll see that the differential equation in every mode is the same. It's x dot of t is equal to 1. Okay. Is this more realistic a model than the other one we had? Is this model time triggered or event triggered? Time triggered, right? So this model is time triggered, but it's time triggered in an explicit way, right? You have a variable that's tracking time, it's tracking real time. So you know that when this transition is taken, 60 seconds would have elapsed, right?
Having a time concept to just have everything instantaneous and for
Okay, so if I understand the question right, the idea is to have bubbles for every increment that you make. Did I get that right?
I'm not sure. Okay. Have a bubble for delay 60 seconds.
For delay. Oh, I see. Oh, I got it. Okay. So let me just draw something and let me know if this is what you intend. So.
Kind of like the rate of the.
So you have a state and you have another state and you have a middle state where the time elapse occurs. So here you have x dot equals 0, and then here you have x dot equals 1, and then here again you got x dot equals 0, something like that. Okay. So so in this picture, you could do something like that. You could break up this mode into a mode where time doesn't elapse, then a middle mode where time elapses, and then another mode where time doesn't elapse. But it would be redundant. Like you wouldn't be adding more information to the model. Okay, so I mean that would be a fine way to do the model, but it's not necessary. Okay. All right. So the advantage of this model over the count-based model is that it's explicitly time triggered, right? So there's no ambiguity about that. It's clear from the model itself, from the picture itself, when transitions are taken. But is this realistic in terms of implementation? Can you implement the variable x? Okay, Rafael? Not as a continuous variable, right? So your x has to, in this case, x is a perfect clock, right? It's tracking time perfectly. So time is, t is a variable that's elapsing. It's global time, right? So that's the perfect notion of time. And here we're saying x is equal to t, right? That's like the perfect clock. No clock skew, right? And no sort of degradation over time, anything like that, right? It's always accurate. I mean, even if you have an atomic clock, it's not perfectly accurate, right? And so so implementing x of t as we have it here, that's not realistic. But as a modeling tool, right, this is fine, because what it's saying is that it's assumed that I have a perfect time, right? Given that, this is how my system should work. And then you have a separate layer to try to approximate that as well as you can. Okay. Ideally, what you should be careful about when implementing that is that if your system really depends on the exact values of delays, then you have to be aware that your timers may not be perfect, and they may not measure time intervals perfectly. So rather than having equal to 60, as we had discussed earlier, you want to have 60 minus epsilon, 60 plus epsilon, something like that. So give it a little bit of tolerance to deal with any skews that you might get. Okay. Now let's do a design problem. So let's see how we can model a timer where the output of the timer is a tick signal. Okay, so it's a pure signal that is generated whenever t time units has elapsed. Okay, so the picture is I want to have an output which is a tick of the clock, and this is a pure signal. And specification is that tick is present if and only if t time units has elapsed since the initial state or the last tick. Okay, so how do we do this as a timed automaton? The hint is you need one mode. What's your name, by the way? Tom.
Let's say for the guard.
Okay, so okay, x dot of t equals 1, and the guard is x of t greater than t. A tick, exactly. So the output action is simply generating a tick. Okay, so that's what you have here. I have s instead of x, and the other thing is to reset the timer, right? You have a single mode s dot of t equal to 1 here, and you check if t time units is elapsed. If yes, you go back, issue a tick, reset the timer, and continue. Okay. Yeah.
Is the notation clear here that the tick is discrete?
So the question is it clear from the notation if whether tick is discrete and when you deassert it? Okay. Now it comes from the type of the tick signal, right? The tick signal is a pure signal, so at any instance it's either present or absent, and if it's not present, then it has to be absent, right? So here on the transition, the tick is present only when you take the transition. And so if you reset this to 0, then you're going to have to wait for t time units again before you can generate the next tick. And in all those time units, tick is not present. Okay. What concrete system does something like this, the model like this, correspond to? Something that we've seen in a previous lecture. Timer interrupt, right? So this is a model of the timer interrupt. It's a little different from the one that we saw. So in the one that we saw, you set the timer to t, then it counts down to 0, right? When it reaches 0, you get a tick, and then it resets back to t. So it's a slight variation on this model. In fact, it's a good exercise to go back and make sure you understand the notation by redoing this model with the timer interrupt scenario that we discussed on Tuesday. Okay. All right. So here's the promised bouncing ball, right? So I told you that hybrid automata can be used also to model physical systems, so with natural phenomena, that is. And so you have a bouncing ball where the ball starts at some height h0, right? So y of 0 is the position of the ball, so it's the vertical distance from the ground. So the ground, this is considered to be 0, and y increases upwards. So y of 0, the initial height where you release the ball from is h0, and at the point of release, the velocity in the vertical direction, so y dot is 0, right, because it's at rest. And then you release it, and in this mode, it's subject to gravity, and that's it. That's the only force. So the differential equation that determines how y and y dot change is y double dot, that's the acceleration, is equal to minus g, right? It's pulling it downwards. So what's going to happen is the ball is going to fall and then hit the ground. And when it hits the ground, it's reached position 0, and it's going to reverse direction. So the velocity is going to change. Okay? So this transition corresponds to hitting the ground. Okay? What happens when the ball hits the ground? So it happens when y of t is equal to 0, and we'll, in order to indicate this, we'll indicate this using a bump output signal. Okay? But what happens in terms of the physics is that the velocity of the ball is going to get set to minus, so it negates the direction, minus a times the velocity that you had when the ball was, at the instant the ball hit the ground, right? Here a is called the coefficient of restitution, right? So this is what determines how much high it's going to bounce back, right? With what velocity it's going to bounce back. Typically a is less than 1, right? Because it's not a perfect surface, right? So it loses some velocity when it hits the surface and returns back. Okay, and so that's captured in this model. Now, this is something you would not think of as a hybrid system because there really isn't any digital control to it, but it's actually a convenient way to model it, right? There is a discrete phase change in what happens to the system. When it hits the ground, then it reverses direction in this way. Okay, so can someone tell me, if I were to plot y of t against time, what would that look like? What is the shape of the curve that I would get? Okay, so it's going to be parabolic, right? So so if you plotted y of t, it would look something like this. So it starts at h0, and then it decreases until it hits the floor at some time t1. Simultaneously, if I plot y dot, the velocity starts at 0, and then it's moving downwards, so the velocity is negative, and y dot of t is going to be minus gt, right? So it's going to go down, and it'll have some value depending on how high it was when you dropped it, when y of t is equal to 0. And then at this instant, it's going to reverse direction. So really what happens, this corresponds to jumping from this point to that point. Okay, and the size of this is going to be minus a times whatever this value was, okay, when it was moving downwards, and then the process repeats. Okay, and so if a is strictly less than 1, then you will get these parabola of decreasing height, because each time it bounces, it's going to bounce back to a lower height than it was the previous time. Okay, so it's actually a fun thing. LabVIEW I think provides you with modeling for these kinds of systems, but if not LabVIEW, there are many other tools out there that can do it. It's a fun thing to actually go and create this model and simulate it and see what happens, right? And sometimes if the modeling tools haven't done it right, you'll see weird numerical effects, like the ball goes through the floor, right? So that happens actually. So it's worth doing this experiment. Okay. So one more thing. So now in a hybrid automaton, So we talked about if for a finite state machine when the transitions, when the reactions happen, right? They happen either they are time triggered or event triggered and things like that, right? Now in a hybrid automaton, when do reactions happen? So reaction is a change of state, right? So when does the reaction happen in a hybrid automaton? Constantly, right? Correct. So the reaction happens constantly because here x dot of t is varying according to this differential equation, and so the state is actually changing. The value of x is changing. Okay, so reactions happen continuously. The continuous variables are always being updated. Even when x dot of t is equal to 0, right? I mean, you still have the continuous variable. It's following that differential equation. So the reaction is still happening, except it's not changing the value of the variable. It's a stuttering reaction. Okay. All right. So there is a bit of a subtle issue that happens in hybrid automata and even finite state machines. So here we talked about this case where what happens if x is absent. If the transition is enabled when x is absent, and so suppose you say that this is time triggered, and this transition is taken as soon as this holds, then as soon as you enter S1, if x is absent, you would immediately take the transition, right? So this transition is enabled at the earliest time when x is absent, after you enter that mode. So now what happens if x was present when you entered the mode S1, that instant, and then just a split instant later, x is absent, right? So it's like you have this infinitesimally small amount of time between when you entered mode S1 and when you took that transition. Okay. Now, if we try to model this, it gets complicated because we don't know what the delta is, right? I mean, if it happens as soon as you enter that mode, but what is as soon as, right? There's actually a fun example of this that happens in physics. So how many of you have seen this device, the Newton's cradle? Okay. So you have 5 metal balls here, and you pull one of these balls and let it go, and the 3 in the middle will just stay as they are, and then the 5th ball will move, right? So the 3 balls in the middle stay at rest, but momentum is transferred from the 1st ball to the 5th ball. Okay. Now this is a kind of weird thing because all the balls in the middle are at rest and they have velocity 0, so the momentum is 0, right, throughout. And yet there is transfer of momentum from the 1st ball to the 5th ball. Therefore, there must be a split second where the momentum of the middle ball is non-zero. Okay, so this is an example of a system like the one we had earlier, where the value of some state variable or output signal is 0, and then infinitesimally later, but we don't know how long later, it becomes non-zero, and then immediately it becomes 0 again, right? And it's a real system, but we have to be able to explain it, what happens, right? We need a good model of that. Okay, so so the way this is modeled is using something called super dense time. Has this been discussed before in the class? No. Okay. So the way you talk about this is you say time has not only the traditional time t, which varies over the reals, which you use to describe time instance, but also at a given time instant, there are so-called, you can think of sub-instances, which I can describe with natural numbers. Okay. So now at every time t, you have, let's say at time t comma 0, that's a 0, let's say that the momentum is 0 of the ball, but at t1 the momentum becomes non-zero, and then at instant t comma 2 the momentum returns to 0. So it's all at the same physical instant of time, right? But just to explain the phenomenon, it's like you have a change in the state of that ball when it goes from 0 to non-zero to back to 0. Okay, this is just is a model to use to explain this, and there are other ways of explaining it. And there's a whole page in the book that talks about Newton's cradle and superdense time, as well as alternative ways of modeling the seemingly contradictory situation. Okay, any questions? All right, so see you guys on Tuesday.